In this video, we are going to explore using some familiar trigonometric identities to solve some common types of integrations involving trigonometric functions. Listed below are some trigo identities which you have come across during your secondary school years, and you are expected to have knowledge of all of them. Unfortunately, only the second set of equations are given in the MF26 and you have to memorize the rest. One easy way to memorize them is just simply memorize the first and the third, and you can derive the fourth set very easily. So from the third equation into the first equation in the fourth set, what we have to do is to simply divide throughout by cosine square theta. And to get from this equation to the last equation over here, we simply have to divide across throughout by sine square theta. Now, let us take a look at some examples where each of these identities are being used in various cases. The trigo identity sine theta equals to tangent theta times cosine theta is commonly used for the integration of either tangent theta or cotangent theta. For example, in part A, to integrate tangent theta, what we can do is to simply rewrite tangent theta as sine theta over cosine theta. And now we can actually observe and see that sine theta is actually negative differentiation of cosine theta. And that means we can make use of the formula integrate f prime x over fx equals to ln of fx to help us integrate this term. And let's first rewrite this equation as integration of negative sine theta divided by cosine theta, and I have to add a negative sign outside to balance the entire equation, and therefore this will give us negative ln of modulus of cosine theta plus c. You can try out part B on your own using the same trigo identity. Next, the diamond angle formulas are most commonly used for the integration of either sine square theta or cosine square theta. For example, to integrate sine square theta, what we can do is to first rewrite sine square theta in terms of cosine 2 theta. So based on this equation over here, I can rewrite it as sine square theta equals to 1 minus cosine 2 theta divided by 2. And therefore, this integration can be transformed into integration of 1 minus cos 2 theta over 2 d theta. And these two terms inside the integral are very easily integratable, and I can integrate them to give us half theta minus 1/4 sine 2 theta plus c. You can try out part B on your own using this same technique. The Pythagorean identity of sine square theta plus cos square theta equals to 1 can be used for integration of higher powers of sine theta and cosine theta. For example, to integrate sine cube theta, we can rewrite this term as integration of sine square theta times sine theta. Next, for this sine square theta over here, I can rewrite it as 1 minus cosine square theta. So let's make the change now to get 1 minus cosine square theta times sine theta d theta. And to solve this integration, we have to first expand everything out to get integration of sine theta minus sine theta times cosine square theta d theta. This first term over here, you have no issues integrating it, it will just give us negative cosine. But for this second term over here, we have to observe and try to link it to our formula of integrating f prime x times fx to the power of n dx equals to fx to the power of n plus 1 over n plus 1 plus c. So we can see now very clearly that the cosine theta is our fx and our n is 2, And therefore, because fx is cosine theta, our f prime x should be negative sine theta, which we have it over here. And therefore, these two terms can be easily integrated to give us negative cosine theta plus cosine cube theta divided by 3 plus c. The final set of trigo identities can be used for the integration of higher powers of tangent theta and cotangent theta. For example, to integrate cotangent square theta, we can rewrite it as integration of cosecant square theta minus 1. And we can integrate both of these terms very easily. For cosecant square theta, we will end up with negative cotangent theta, and for 1, we simply get a theta and have a plus c at the back. Next, for tangent cube theta, we can rewrite it as tangent square theta multiplied by tangent theta. And for this tangent square theta, I will be able to rewrite it as secant square theta minus 1 multiplied by tangent theta, d theta. And if we expand these two terms, I will get integration of secant square theta times tangent theta minus tangent theta, d theta. And how do I integrate both of these terms? For the term on the left, you can see that this is my fx, and it is to the power of 1, and this is my f prime x. And for the second term, for tangent theta, I can write it as sine theta over cosine theta, and therefore integrating these terms will give me tangent square theta over 2 plus ln modulus of cosine theta plus c.